Then welcome to lecture, I believe it's 5. In parallel and distributed computing. So today we talk about your homework. So this course includes a project that you're supposed to do with MPI. Now we have done a little bit of introduction in C++ and MPI, and now we come to what you are supposed to do. And of course there is some, arrangements that you should follow. So first of all, this is a project that is done in groups of 2. Yeah, so currently I think it would just match up with, I think there's one colleague is missing. We are probably 9, right? Okay, but anyway, so you're expected to form groups of 2 people. In TUBS-IRMB, there are groups where you can enter your names together, and then you will be group 1 to 8. Yeah, and then you also have there a folder where you can put your results later. I uploaded to TUBS-IRMB. I uploaded a zip file which includes already the program that you are going to implement in serial format and some files. I would say, yeah, I cannot say template because template in C++ has a specific meaning. So there's some more or less empty files where you can put your stuff in and implement the MPI version. So you will find there several files because you could do it in several ways. There's also you can also implement OpenMP and in CUDA and so on. So they are all in there, but the homework is to implement it in MPI. Yeah, this is the homework. You can do all the others too, but that's, so to speak, this is not the thing that is requested. So then you have time for this until 14th of July, which is a Sunday. So we put the deadlines on a Sunday, which does not mean that you are supposed to work on Sunday. It's just that I say I'm not looking into it on Sunday. So you have the weekend, if you will, to finish it, and then I look into it on Monday. Yeah, and then in that week, you can put an appointment from the wiki page where you put again your names, where you do a presentation of your project. I mean, you explain your project, and when this is okay, you pass the project. There is no mark on the project. Yeah, it's just you have to. It's part of the course that you do the homework, but the mark will only be on the exam, and we'll talk about the exam dates later in the exercise. Okay. So you will hopefully find these things there. If you have a problem, then ask us. And now let's have a look on what the problem actually is. So we are here interested in physical simulation, usually. And we take an example that shows many things that you have to know when you do physical simulation in parallel programming, with an example that is extremely simple from the numerical point of view. Yeah, so that you do not have to focus on this part. And the idea is that we compute the heat distribution in a plate. So a plate is something two-dimensional, yeah, so it has x and y coordinates, but it has no thickness, so to speak, so it's no set coordinate. And this plate has boundary conditions, so there are there are 4 different sides of this plate, and each of the sides has a different temperature. And there's a homogeneous material, and now we want to know how is the temperature distributed inside this material. So this is a physically very simple problem to solve, or numerically very simple problem to solve. But it has all the components that we also need for more complicated kinds of simulation. So, okay, we need the problem statement itself, which is, of course, the partial differential equation, the one up here. So the change in temperature, so dt, this means change in temperature with time, partial differential equation. So there is, there is one dependent variable, which is here called u, as it is called in the code, I believe. So actually, I don't remember why we called it u, but this is supposed to be the temperature, yeah? And then there is a diffusion coefficient that we call k, and here we have a so-called Laplace operator. Laplace operator is the second derivative of the quantity in x plus the second derivative of the quantity in y, and usually if it is a three-dimensional problem, there would be the second derivative of the quantity in z also, yeah, but because it's two-dimensional, this will drop out and we just have these two derivatives here. So since you are studying, or many of you are studying CSE, you should be familiar with finite differences and how to implement them. So finite differences, second finite difference can be implemented like this. Anybody here who has never seen a second order finite difference? So you came to my numerics class, right? No. Did you attend my numerics class? No.
The first semester here.
The first semester here. Okay. So some people have not seen a second finite derivative. This lecture is not about finite derivatives, so I don't want to explain this too much. But you know, finite derivative. I mean, you know what a derivative is, yeah? And the derivative in the school, you sometimes see it like this. You get the quantity on the left side of the point where you want to evaluate on the right side, and then there is this distance between the two where you divide by, so you get a differential what's it called? Ratio? No, it's a quotient, differential quotient. Why don't I know this in English? Yeah. So you have the difference between two values at two different points, and you divide by the distance. Yeah, and then you take the limit of the distance going to 0, and so you come to the derivative. So you've seen this in school, right? Yeah. So this is, and then for the second derivative, you do this more or less twice, and this is what you see here. So there would be a right derivative, ut minus ut at the position x plus h minus at the position x, yeah, and then the one on the other side also ut minus and minus this again, and then you do this again, the same derivative again. So now you have two derivatives on 2 points, and then you take the derivative again between these 2 points, and then you end up with this equation here. Or do you need a very detailed? I think this is enough. So this is the equation where you compute, with which you can compute the second derivative numerically. This is the one in x, and this is the one in y, second derivative. And now you want to approximate this differential equation here with both the central finite difference in space and with a time integrator. And the time integrator, the simplest time integrator is the Euler forward method. So then I have to ask again, who has never heard about the Euler forward method? Okay, you heard about the Euler forward method. No? Okay, so the Euler forward method. So this up here is the discretization. Did you have any partial differential equations in mathematics?
I think I did. That was 3 years ago.
3 years ago, yeah. I always tell you that for me it's 30 years ago, yeah? Okay, maybe it's only 25 years ago for me. Okay, so this is, I'm also teaching a numerics class, so I always probably you guys don't need to attend this, so because we do this we teach this in the bachelor, yeah. So therefore I don't want to go too much in detail. The Euler forward method is a method to do the time integration. Yeah. So here because you see here we have second derivative in space. So we have to identify what is the second derivative in space, and then we have the first derivative in time. Yeah. And in order to get the first derivative in time is kind of a little bit more difficult, or no, difficult. I mean, it's different from what you do in space, because if you take a derivative in space, you assume that you know your left neighbor and your right neighbor, right? If you have this derivative in time, then usually you only know the past and not the future. This is why here we use a one-sided finite difference. Yeah, and this one-sided finite difference, and this is kind of written. Do something that is not useful for the. So you go to so t plus delta t. Yeah. And you do this minus ut, and you divide this by delta t. So this is your approximation of dt ut. Yeah? Right? So, and now you take the dt, so you take the dt to the other side, so it will end up here. I mean the delta t, so sorry, the delta t, you put the delta t on the other side. And then you also put this ut also on the other side, and then you can compute the next time step from the current time step. This is what Euler forward does. So now you combine these two things, or the three things, if you will, all together to build. So you add up these guys here. Yeah.
It's a numerical formula. No, I got it. Sorry, it was just me.
Okay, so you put all of these things together, and then you make the clever decision. Good morning. You make the clever decision to choose the time step according to the grid spacing, which now here is h square, divided by 4k, and then everything drops out. So the reason why we can do this is because we are interested in the final state. Yeah? So we don't care about the actual time resolution. Yeah? We can just choose our time step such that everything here drops out, and we can simply write it like this. So by the way, you see in here there would usually still be this ut, 4 times ut, yeah, minus 4 times ut, but because there is this ut here without 4 times, yeah, it's dropping out. And so in order to see what happens after a very long time, so in the steady state, all you need to do is to take the 4 neighbors, to iterate, but to take the 4 neighbors around you and update the state as the average between the states of the 4 neighbors. Yeah? So this is more or less the simplest way of solving such a problem. You see, it does no longer depend on the grid spacing. It does not longer depend on the diffusion coefficient, and no longer on the time step. Yeah? So this all we have eliminated all of this, and now what we can do is we can iterate this function. We can start from an initial guess, and we iterate from this over this function in order to get to a better solution. And once the solution does no longer change, we are done. Yeah? And so this is the picture what we want to see then later. Okay. So this is the physical problem. Now, how to implement this? Even though we are not using SIMD here, but one thing that you usually want to do is you want to treat, the simple thing that you would like to do is to treat all the points in your domain in the same way. And there's always a question, how do you implement the boundary conditions? So what kind of boundary conditions is this anyway? Is this a Neumann or a Dirichlet boundary condition? There's a Dirichlet boundary condition. Who does not know what a Dirichlet boundary condition is? Okay, several people don't know what a Dirichlet boundary condition is. The Dirichlet boundary condition is a boundary condition where the value of the function that you are seeking, which in this case is the temperature, is given on the boundary. Another type of boundary condition would be the Neumann boundary condition, where the flux of what you are looking for is given. So, for example, the stove. There are nowadays modern stoves that do it better, if you will. But the stove in your kitchen is a Neumann boundary condition, yeah, because it is not such that you press a button and you set the stove to 120 degrees, yeah. Instead, your stove is set to a certain amount of heat that is provided. So, for example, it has 800 watt and 1,000 watt, and so on, yeah. So it's the amount of heat that it's providing, yeah, and this is then the flux, a flux boundary condition, and not the Dirichlet boundary condition. But I believe nowadays with modern technology you can also buy a stove where you put the temperature, and then you have a Dirichlet boundary condition. So the Dirichlet boundary conditions are kind of more difficult, Neumann boundary conditions would be more complicated to implement. So we'll do it very, very simple and just use this Dirichlet boundary conditions. And Dirichlet boundary conditions can be implemented just by extending our domain with what we call a ghost. No, do we call this a ghost layer? There's a layer around the domain with points where we just input the values of the boundary and we'll just keep them the same all the time. So we'll not update these things. So we'll do the update here in this inner part here, which we call inner grid. And then there's the entire grid, and here are grid cells which are not updated, and here we input our boundary condition, and then we iterate only over the inner grid. Okay, so now that's more or less what you're supposed. Okay, so what the problem is, and now we talk a little bit about some things that we have to consider if we want to solve these partial differential equations, if we do want to do simulation. So, general feature of most partial differential equation in general, and in particular the ones that are partial differential equation in space, like this one here, even though it's only two-dimensional, is that we somehow have to deal with the fact that we have multiple dimensions. Yeah, so you have actually coordinates of points that have to interact with each other. So first they have to interact with each other, and second we have to iterate over these points. And if we want to iterate over these points, then even in two dimensions, we have two possible ways we could do it. Yeah, so, I mean, since we always have a sequential part in our program, yeah, we can now either iterate over the columns. We could iterate over the columns. I mean, it's funny when I say iterate over the columns, then this means we are iterating along a line, right? Or we can iterate over the lines, which means we are iterating along a column. Yeah? And this is kind of a little bit confusing. So I don't know how many times I will miss, I would just say it wrong today, yeah, because I have to keep myself under control, that when I say we are iterating over columns, it means we are iterating inside a line, yeah, and if we iterate over a line, we are iterating over columns. Okay, so there's this difference. Now the difference being in terms of the program is that we have two loops nested inside each other, and of course you have these two possibilities, namely that you have the outer loop over x and the inner loop over y, or the outer loop over y and the inner loop over x. So what difference is this? The difference obviously is that the inner loop is the fastest. Yeah? So this is where the index changes the fastest. Okay, so why does this matter? Any question? Any question? No. Why does it matter? It matters because computers are fundamentally one-dimensional. In data, so data is always stored in a one-dimensional format in your memory, and we have learned that in order to be fast, we should always access data sequentially in the way it is stored in the memory, right? So, now how is this actually done in a C style, in usual C style arrays? So, for example, you can, that would be a static array. So, at compile time, the size of the array is, the size of the multi-dimensional array is known. Yeah. So, for example, you put an int a with 3 rows and 4 columns. Yeah. And then you would define it like this. Yeah. So you would write the 0 row first, the row 1 second, and then third the row 2. And the same thing can also be written like this, because what a C simply does with this here, it unrolls this multidimensional thing and puts it in a single row. Yeah? So this is the same for C. So this here is how the matrix A would then be stored. Yeah. So if here we have here the elements 0, 1, 2. So, and in the mathematical way of writing it would be A11, A12, A13, and so on. And the data would be stored, yeah, in the row first. So we'll store the row first. Yeah, this is the first row. And because the row is stored together, we call this row major. Yeah? C and C++ is a so-called row major programming language because the rows are stored together. We start with the rows. But this is important to know because this is not a universal truth. Because there are other programming languages that do it the other way around. So again, this here, so row major, so this matrix here, row major, would be stored like this. So the first row followed by the second row. And this is done in all the programming languages that somehow has a C in their name. No, okay, Octave has a C in their name too, and Scilab too. But the programming languages that are based on C. Yeah, so there's C, C++, C#, Objective-C. Yeah, they have this row major way of doing stuff. And then there are things that are nowadays also quite common. So, okay, Fortran, okay, I said Fortran. Fortran has been common for a long time. Probably it's no longer so common nowadays. Fortran, MATLAB, yeah, Octave, okay, MATLAB and Octave, they are of course compatible. Julia, SR, Scilab, yeah. So they don't want you to think in C style. They have so-called column major. So they store the first column followed by the second column followed by the third column. And the funny thing, what this means is, if you, writing the same program in these two different worlds will lead to one being in the right order and the other one being in the wrong order. Yeah, so knowing how it is stored is important, that you write your program in the right order. Yeah? So, right order. what does it mean? So if you have now instead of these static C arrays, so what you will usually do in C++ or also in C, where you do not know at compile time how large your array would be, as you would have a dynamic array, and this you do by having an array with pointers to another array where you then have arrays where you then have your data stored. Yeah, and now in this example, you put in the x direction, you put the pointers to the arrays in the columns, and now it's the question, how would you address these things here? Now, for example, if you iterate now over the x direction, then you would ask for one datum out of the different arrays each time. Yeah? So because they are connected inside this array here. Yeah, so they are connected in y direction, but they are not connected in x direction. So basically, a cache line would always be aligned here with the y direction, and it would be misaligned with the x direction. So if you iterate over x, so you have x as an inner loop, then every time you read or write something, it will be misaligned with the cache. Whereas if you have y as the inner loop, then it will be aligned with the cache in this context. Yeah? But it always depends on how you build your system, and I'm addressing this because inside the example that we are going to use, we have implemented this in a different way, and this is also often done in in scientific software. So we'll come to something in a minute that's called mapper2d. So this is a function that is implemented in the example for your homework. And what we are doing here is we use a one-dimensional array to store the two-dimensional data. Yeah, so we don't need to have that many pointers. Yeah, so we don't need an array of pointers. Yeah, what we do is we put everything in a one-dimensional array, and then we chop it off, yeah, and put it together again. So more or less we do this by hand. And if we do this, we have to take care which is the fast and which is the slow index. So of course this depends entirely on how we implement it. Yeah? So in this case, it is now implemented in this way that we like to iterate over x first, and this is something that we see if we look into the class mapper2d now in particular. So mapper2d, what it basically does is it implements this, it has more functions, but the most important function is the following. So we have one big data array where we have all our data in it, And this data array has only one index because it's a one-dimensional array. And from this, we want, for this, we need for our coordinates to know where the point is. So we need a function that takes the coordinates of our point and gives and returns the position in that array. And this is obviously done like this. So there is an nx, which is the number of, which is the number of columns. Yeah, so the size in x direction. Yeah, so the chunks that we cut off. Yeah, and now you see that here we iterate over x. So if we increase x by 1, we get to the next neighbor. If we increase y by 1, we go another nx to the right, for example, right? So then obviously here, the index that you want to iterate innermostly is the x index, yeah? Because here you always end up with your immediate neighbors. So the same is also in reverse. So given your position, your position in the array, yeah, so this is what we call the position. That's the position in the array. We want to know your coordinates, and the coordinates, of course, can be computed like this. So what does this? This is position, and it takes the what is this? It's just missing my words. The modulo, the position modulo the length of one row, yeah, gives you the position in x, and y is just this integer. By the way, why does this? So yeah, the y position is the position divided by the length of a row. Why does this here actually work? What is this strange programming language that does not allow to have integer? Lua, right? Can you do this in Lua? So this is nasty question. So what does this operation actually do? Okay, so say my position is
It doesn't necessarily return an integer.
does it? You know, this is the luxury of a well-typed language.
It
Yeah?
return an integer because the function is returning an integer.
It's returning an integer, yeah. So you all have the fate that you grow up in this age of scripting languages and Python and all this ugly stuff. So in a properly typed language, this here is an integer division. See, you divide 8 by 5. 8 by 5 is 1, okay? Because we made absolutely clear that all of this is integer. This is why we can do it like this. Okay. So this is part of what we are going to do. So now I will not demonstrate it right now. If you have any problems with this, we'll do it in the exercise again. Probably not today. But here's the way. Here's the way to actually do it. So first and foremost, you have to place the Laplace 2D example in your own folder. Yeah. So, and don't mess up with the folder of your colleagues. And always remember, everybody can look into your folder, so everybody can steal your homework and mess up with your homework. I don't know whether it is a terrible problem that everybody can steal your homework, but also remember that everybody can mess your homework up if they just go in and try something out. Yeah, so keep your homework somewhere safe. Keep your homework somewhere safe. And also, this is also the reason why there is no mark on the homework. Because if you steal otherbody's homework, yeah, I don't want to be involved in this. The thing is, you have to present your homework and explain it to us. Once in this demonstration. This is how we assume that you actually were involved in doing your homework. Yeah? Okay, so, but please try it yourself. I mean, is like, the big thing is, all of this will be part of the exam. Right? So, this is the best exercise I can give you. Okay, so you are supposed to go into this folder and make a folder build. Then you go into the build folder, and then comes a little bit of tool chain, if you will. That if it's not clear, we'll go over this point in the next exercise. So we have to, I should say the following. This program is made up of several files, not many, yeah, but we are practicing here for actually real world things where we have a lot of files, yeah, and there you need to have some tools that simplify your compilation. And this is usually in the Unix world, this is done with make files. But the make file has to come from somewhere too. And the make file is generated by a tool that is called CMake. And the idea behind this CMake is that it prepares all the infrastructure for making your program run, and this across different platforms. Yeah, so there is some input file for the CMake already in the folder outside the build folder, because the build folder is of course now a new folder. You go into the build folder and then you call CMake with the outside folder. This is where the two dots are for. Yeah, and then it will generate the make file and all the other files inside the build folder. So this is the way you usually do it. You could also go in the outer folder, call CMake there, and then make, and then the problem is, or maybe there's no problem, but it will generate all these files inside the root, not the root folder, but the outside folder where also you have your C++ files and so on. Sorry. And the disadvantage of this, or the advantage of using a build folder, is that when you want to get rid of all the stuff and do everything again, you can simply delete the entire build folder, because everything that has been generated by the build process is in the build folder. Yeah? So, and only that stuff. Yeah? So this is why we use build folders. So, right. So you're supposed to be able to run the Laplace serial version. So this is the example. Simply like this, after you build it, of course. And then there is something that you should actually then use, namely the sbatch command together with the job file, which I believe is also already included in this. So what is this for? So far with the simple examples that we had, is we compile our code and we run it directly on the how they call the login nodes, which is something that you should not do. Yeah? So this is something that we do only because we use very short programs. Yeah? But here, Phoenix is a batch system. Batch system means there are all these compute nodes, so there are the login nodes that allow you to get onto the computer and do some stuff like probably compiling or giving some commands, and in particular giving commands with to the batch system. So the batch system, these are the actual compute nodes. So there are many compute nodes of different versions. So there are so-called fat nodes that have a lot of memory. Usual compute nodes with average memory, I guess. And then there are other nodes with GPUs. Yeah, so, and they have different so-called queues. So now what you do in a batch system is you put your program in a queue. Then it will wait in this queue until one of the compute nodes or the resources that you requested are available, and then it will put it on these resources and process your job, and then your job will be done later, and then you can pick up your result. So, concerning the resources that you requested. In a batch system, like Phoenix, you cannot just request one node, for example, one compute node, but you can specify the number of compute nodes that you need, because you have a distributed problem. Or you have, for example, you have a big problem where you need a lot of nodes, a lot of MPI processes, or you may have many small problems where you need only one node, or where potentially several programs could run on the same node. Yeah, then you need fewer resources. So I now need only say one node. I need 5 nodes, and so on. And then this you can specify in the job file. And now, depending on what resources you're requesting, you get processed more quickly or less quickly. So usually if you require less resources, then you could get your job done more easily, because if you request the entire cluster, yeah, so you have to wait until the entire cluster is free, obviously, yeah, and you anyway have to wait because you also have a priority attached to you. So this is why we use the job files, and I guess we have to practice this before we actually do this, and this, I guess, because we have another exercise today, but we could do this next week. And so, guys, I know next week is a holiday, but the Friday is a usual, the Friday is usual lecture, yeah. So please come and enjoy information about how to use a batch system, yeah. Okay. So I remind you, the exercises are not going to be recorded as always, yeah? So, okay, let's come to how this can be done. You can do it in another way, but this is the way it's usually done. So, for solving partial differential equations in parallel, the technique that we are usually using is called domain composition. The domain decomposition. Which means you have a system of certain size, so in space, and you attach, so you cut this into pieces and you attach certain parts of the domain that you are simulating to different processes. So the processes here, and the MPI processes, they are grouped according to their rank. So we start with rank 0, and we have rank 1, rank 2, and rank 3. So since we have a square, the easiest thing that you can do if you have 4 processes is to cut it into 4 other squares. Yeah? There are other ways of doing it. For example, you could cut it in 4 slices. So why would you usually cut it like this rather than like that? Any reason, or is this just arbitrary? It doesn't matter.
Because of the memory or how it works in the storage. It makes sense.
Okay, so if you don't like to cut it, you could also cut it that way.
You could say that one which is efficient with communication,
Aha, so why is the one efficient with communication?
like if we have a minimum amount of communication, then
Ah, okay, right. So, this is really an art, yeah? Because it is not a priori clear how you minimize your communication, how you arrange your domain in order to minimize communication. And it's also not clear whether minimizing communication is always your goal. Yeah? Because there are other constraints that could play a bigger role. But minimizing communication is usually a very good heuristic, because communication usually is the most expensive stuff that you are doing. Depends on your problem, but it is usually the expensive stuff. So, and therefore, what you could think about an heuristic is the minimization of the interface, right? Less interface means better. Yeah, less interface usually means better performance. I'm just thinking, let's see. Would we have less interface if we cut it this way? Probably even not. Yeah. So, by the way, we have here one. Okay, we'll see this in a minute. or maybe now. So who in this configuration, who is communicating with whom?
0 with 1,
Mm-hmm.
0 with 2,
Mm-hmm.
1 with 0, 1 with 3, 3 with 2, and 3 with 1, and 2 with 3, and 2 with 0.
2 with... Yeah, okay, I hope I got all of them. Yeah, so what is this about? Is 0 communicating with 3?
No.
Why not?
No, it can communicate because it has a node which is required.
Okay, so the thing is, if we go back to our example, and this is actually visible, it's not a good color. So we are just taking this neighborhood, right? Yeah? So, but there are other numerical methods that use a wider neighborhood than that, or that would also take the diagonals. And if you take the diagonals, then it's no longer so simple. But this brings me to something else here. So actually, you see, if I put it is actually, in this case, it apparently wouldn't matter if we would cut it just in x direction, apparently, yeah, because the length of these lines would be the same, right? But there would still be a problem with this. So what is the advantage? Let me see whether I can potentially so we could cut it like this, right? So what would be the disadvantage of doing it like this compared to the other, to the one that is on the screen already? So the interface has the same size, yeah?
The interface would be larger.
No, the interface would not be larger. Is it because we are just turning this line here, yeah? This is the same size.
But there will be no interface between the last line and the first one.
Yeah, so there would be no interface between the last and the first, yeah? Which means? Yeah, so see, the one in the middle. Okay, so I did not. Okay, so first of all, the one in the middle should be say now. Okay, so I did not partition it in an equal way in this way, because the one in the middle, the way I draw it, would be the one in the middle would be. No, wait. We need 4. We need 4. Wait. You are right. We do it in 4. Right. So if you I'm so stupid. Yeah. So if you do 4, you have 1 line more. Yeah. But anyway, I wanted to say so. So the reason, yeah, it would increase the work, but it would also do something else. So I wanted to address something else. So in that case, the one in here, or the 2 here, these 2 here, they would have to communicate with 2 sides, whereas the outermost would communicate only with 1 side. Yeah? And that would mean that the ones in the middle have more to do than the ones at the end, and so they are not well balanced. So the one outside, they would have to wait for the others. So it's better to have a better balance, but also, yes, okay, sorry, and in fact the interface would be larger. Okay, so we do this partitioning, and then we think about the communication. And for the communication, we are using now the technique of ghost layers. So ghost layers, almost, I believe I just stopped myself. I almost used the word ghost layer for the boundary conditions. Yeah, because we also put a layer around there where we put our boundaries. And now the ghost layer is a copy of only the outer layer from one process on the other process. So, because you can think about it the same way as a boundary condition. Yeah, so this domain here in rank 0, this partial domain here, is missing two of its neighbors. So, in order to hide that it's missing this, we need to set a boundary condition around the inner part of this rank 0. So we enlarge the system by one line and we copy data from inside the neighboring process into this ghost layer now. Yeah? And the ghost layer acts as a boundary condition. So, and we do this in all the different directions. So wherever we cut, we have to implement these ghost layers. And then we do the communication, where we'll do the sending and the receiving. So, and this goes now here in all directions. And if you look at this picture and you see that they are, that in a sense they, again, as last time, they have here more or less a loop, right? So this is why we addressed this so-called philosopher problem last time, because you see, you can stop yourself from going forward by not arranging who is going to receive and who is going to send the data. And I mean, you have to imagine now that we only put 4 processes here, but this could go on, further, yeah. So there could be 10 processes in one line, yeah, and the one is sending to the left, and the next one is sending to the left, and they are waiting to receiving, yeah. So how do we solve this problem? Again. Yeah, so we have to distinguish between the indexes between odd and even. Yeah, and one sends first and then receives later, and the other one the other way around. Okay. So the way it is supposed to be done, and now in this picture, so the previous picture was just the communication with 4 processes. Now this here would actually the way this is now displayed would also work with processes all around it. Yeah. So you have these nodes or cells with data at the boundary of your inner process, and you have to remember this is not of the inner domain, and this is only part of the physical domain. And all of this has to be sent to their neighbor. So what you have to do is you have to collect the data that you want to send to your neighbors. And you see also some of this data also has to be sent to neighboring neighbors. To neighboring neighbors. I mean, to multiple neighbors, yeah? To neighbors which are neighbors to multiple neighbors. So usually it's not that easy to simply specify the inner part here as a send or receive buffer. Yeah, that would only, I mean, just using this as the send buffer itself, yeah, won't necessarily work because the send buffer has to be continuous, obviously. Yeah, so what you will usually do is you take this data out and put it in a send buffer. So you have a dedicated send buffer, and then you'll do the communication with this send buffer. Yeah, so this is more or less the envelope where you put your letter into, right? So then also you get a receive buffer here all around your system. So you do the sending to your neighbor and the receiving to your from your neighbor, yeah, in sending and receiving, right? So now you have all this stuff. Now you can here imagine what you need to have. So you have an inner grid. You have a ghost grid around here, and then you have the output, the send. You have the send buffer and you have a receive buffer. So you need quite some memory at the surface. Yeah. So you see communication. When I said that communication does a lot of work. It's not only the work that the communication does, but the communication also requires a lot of extra memory. So if you make your domain smaller and smaller and smaller, then you end up having just space for communication. Right. So, okay, once you receive stuff, it has to be copied into the ghost layers, and then you do the computation. So let me see. I guess now this is the procedure, right? So, okay, you start up with partitioning everything. So you know where stuff is, and then you have to initialize everything. You will, for example, initialize the inner part with 0, and in the boundaries you have to set the boundary conditions that are given in the example, and then you do. Yeah, so this is the initial state. Yeah, you set your right, even including the boundary conditions. So, for example, at the top boundary we had 15, at the right boundary we had 9, that we had 0 at the left boundary and 5 at the bottom boundary. Yeah? So we'll put these things, which so the initialization here has been done with the received buffers, which will then be copied hopefully into the ghost layer. You can also start with putting them into the ghost layer originally, yeah, and everything else you can initialize with 0. Then you do the loop over everything. You do the MPI send and receive with the even exchange with the right and the odd exchange with the left. So or the other way around, of course. Yeah. So you distinguish between even and odd. Send and receive. Okay. Then there is one more thing that I wanted to. Right. There's one more thing that I wanted to address, namely. So now you're right. So you are doing the sending and the receiving, and what now you could obviously do is to send stuff and wait until you get stuff and then do the computation. And because communication is very expensive, it does not happen at once. You have to wait for it, and it is usually done in its own thread, so it's handled by the hardware somehow differently, and it involves a lot of waiting. This is usually not the way we do stuff. Yeah? Because the reason why we do parallelization is because we want to be fast. Yeah, so we want to use our big machine well, and we don't have too much time to waste, so we want to be fast. And then, if we want to be fast, we do not want to waste all our time waiting. So now what can we do? We can do something that's called communication hiding. And communication hiding is the process where while you are waiting for the information while you are waiting for your information to be sent and the information of your neighbor to arrive, you do something useful in that time. Yeah? So, your problem here is that you are missing information. So you cannot do any arbitrary computation because you are missing something. So how could you solve this problem? So how could you do something useful when you are actually missing information? Yeah, for example, the data in the ghost layer has not yet arrived. What can you do?
We can first solve the nodes which are near the ghost layer and initiate the sending, and by the sending we can solve the rest of the nodes.
Okay, yeah, but usually the bigger problem is the receiving. Okay, my question, this is correct, but my question was,
Can we send it in the cache?
send it in the cache. No, we are okay, let's try to think about receiving data. Yeah, we want to do computation and we are missing data because this is still, our neighbor has not delivered. Yeah? So, for example, we now are going to do human-based, natural intelligence, as I always call it, parallel computation, because you guys are doing a project together, two of you. So now you do a partitioning, you do this, I do that, and then you are waiting for your neighbor to receive something, but this has not yet arrived. Yeah? So you always have to think then there is an interface between the two, and on the interface we have to wait. We actually have to wait. But then there's also always an internal part that does not depend on the interface. Yeah? And what we are now doing is to split what we want to do in two parts, namely the internal part that is not dependent on the interface and the outer part that is dependent on the interface. So what we would then usually do, and what is called communication hiding, is we initiate the communication first, and once this is done and we have to start waiting, we do the inner part of our computation, where we are not dependent on things that have to, the things from our neighbor. So this is what we do first. So only if this is done, we look whether the stuff has arrived, and then if it has not arrived, obviously we have to wait. Yeah? But because we do the bulk of the work after we initiated the communication, it is pretty likely that the stuff has already arrived once we are done with the big chunk of the work. Because the later chunk of the work will only be done once we are done with the big chunk of the work. So, do the calculations without the ghost layers. All this is what we mean with communication hiding. Now, in the next step, what was actually, okay, so we'll do, so you can exchange also in different directions, I guess. Do the calculation on all nodes that are independent of the ghost layers. Yeah. Right, so I don't, why is this, looks this picture like this? Okay, so what you now do, you will have to, now you have to make sure that you have to wait. But here again, you can distinguish between the different sides of your domain. So you will receive the one in X direction first, or the one in Y direction later. So you also don't need to wait for Y when X comes first. Yeah. So this is a bit be clever in your programming. But here you will need to make use of these wait statements, or potentially also a barrier, but probably better a wait statement. Yeah, where you make sure that provided you are doing your internal work was faster than actually waiting for your neighbor will not kill your program. By the way, this is a very important point. These parallel programs are not deterministic. Okay? So if you don't wait, and the stuff that you use for communication hiding takes long enough, then your program will usually work, even though you did not wait. Yeah? But there is no guarantee, and this is the big problem. Yeah? So the problem is you may not be in a well-defined state. So because that, say, it ran once, or it also ran 10 times, does not mean it runs all the time, right? Because you can just be lucky. In particular with communication time. If your network is somehow busy, communication time can suddenly take much longer. Yeah? So it is not sufficient to assume that you do enough work, and then so you're just doing enough work, so then communication would have to be done, and then data would be here. This is not enough, even though it will usually work, and you will not usually discover by empirical means that you did something wrong. Or you would not discover this very quickly. So your program can be wrong and still run correctly. Okay? Many times. And then suddenly it does not. So this is why it's important that still here with communication hiding you still would use the waiting at the appropriate position. So, yes, so right, so be sure, this is what I was just saying, be sure that everything has been received, and after this you will do, you put in you put in the ghost layers. I'm kind of, yeah. So you put in the ghost layers, and then you do the rest of the computation in the ghost layers. So I find this picture, in a sense, a little bit unfortunate, yeah, because we had to do it like this. This is kind of confusing. If I may just go backward to this picture. So, in this picture, we have drawn this example as small as possible. So there will only be one internal node, right? The inner work will be very small here, while the outer work, yeah, this is when your domain decomposition is too small. Then this is what happens. Yeah, you have one inner node and you have 8 outer nodes, right? So this part of the second part of the work will now take much longer than the first part of this work. But this is not the idea. The usual idea is that the domains are of course much larger, and then they have many more internal nodes than they have external nodes, because the one is the area and the other is just the line around it, right? And in this case, the line around it is larger than the area inside. Okay, so this almost gives us, yeah. Then again, you put everything into your buffers, and you do again you do the loop again. You have to copy stuff in the buffers and send them off. Okay, so now after this, we come to the output part. Yeah, so this again is the sending, and now we come to the output part. And the output part is something that we do sequentially. So there are also, for much bigger problems, there is also parallel data format, what is it called? HM8 something with 5. HEF. AF or EF? Okay, so the HDF5. So okay, for the real big stuff, we use parallel file format. So every process will write out their own file, and then you need special software that can open this distributed file system. For smaller problems, what you usually do is you collect your results in one of your rungs, for example, in rung 0, and this rung 0 does the output. So here again, you need MPI because all the data has to arrive in one place, right? And now this can then be used by this all to all. So, like for example, a gather communication. So the process the rank 0 process collects all the data from all the others and puts them into a single domain, and then it writes out this file in this parallel view format. And when we have done this, we should be done with our homework. So maybe some famous last words. There is, so we'll write out this data in a specific format that can be read by a software that's called ParaView. Yeah? And anyway, what you have to do anyway, you have to download your result from the cluster, because you're not able to visualize your result on the cluster. Yeah? So you have to download it, and then you have to install in your own computer. I guess you guys all have an own computer. You have to install the software called ParaView in your computer, and this can be used to open this file and visualize your results. So these are the famous last words. Maybe if you have any problems, okay, I should have not written it here. Yeah, so the software, oops. But today it's not easy for me to write something. So it's Parallel Visualization Toolkit, ParaView. So this is the W. Yeah. Okay. If there's any problems getting it, then we can of course help with this. I've now not put a link to it here, but it's free software that you can download and install. Good. Any questions? If not so, then I'm going to stop the recording first.